last session on molecular geometry, we discussed the structure of a molecule in group 2 that produced beryllium fluoride or beryllium difluoride. And we found out that this was the unusual thing about this molecule was its geometry was linear, and that there were only 4 electrons around the beryllium core, the outer electrons rather, not the core. And this is not an octet. This is not a noble gas configuration. So even though this was stable, this is called an exception to the octet rule in forming molecules. Well, we're going to look at another exception. This exception is boron trifluoride. Boron, you notice, is in group 3. It has 3 valence electrons. Each fluorine has 7. There are 3. That's a total of 24 electrons. So beryllium, in terms of a Lewis structure, remember we just go 90 degrees here, should have a minimum of 1 bond. We'll subtract out those 6 electrons, and that gives us a total of 18 electrons. We'll assign those 18 electrons around the outer atoms initially. 6, 6, and 6. That's 18. There are no electrons left to go to boron. So it is at this point not an octet. This molecule is valid, and we can show some of the character why it's valid by looking at the formal charge. Boron starts with 3 valence electrons and ends up with 1/2 of these 3 bonds. So it ends up with the same number of electrons after bonding. 0. Formal charge. And here fluorine is 6 plus 1, 0, 0, 0. If we examine, say, well, let's see what happens if we make boron with an octet. That means we're going to have to take a pair of these electrons here and share them and form a double bond, which we're allowed to do in terms of Lewis structures. So we end up with this structure. And here's our 2 electrons. Well, I better color them in with a green. That's our 2 pairs of electrons here. Fluorine with 6 pairs of electrons. Let's look at our formal charge of boron. Boron was 3 initially. Now it's 1/2 of 1, 2, 3, 4 bonds. It's in excess. It is a -1 formal charge. Fluorine here starts with 7. It has 1, 2, 3, 4. Half of these 6 deficient 1 electron. These are 0. So this structure has the most electronegative element in the world as a +1. And boron, of course, minus, which is no good. So this molecule defies the basic rules that the most electronegative element should have a formal charge of -. So this structure we're not going to use, and we're going to stick with the boron trifluoride. Now let's go to the geometry. Boron, central atom, is surrounded by 3 bonding domains. 1, 2, and 3. And look how I drew them. 3 pairs of electrons will separate from each other by 120 degrees. And that creates the minimum repulsion between these pairs of electrons. And of course we have fluorine here. So boron trifluoride is this triangular shape, and it's flat. The name, and I don't want you to forget this, the name of this shape is trigonal, just a fancy word for triangle. Trigonal, and on one plane, trigonal planar. Now, continuing with this concept of the trigonal planar, we're going to take a molecule that you've heard a lot about, but you may not know about its bonding. The molecule is ozone, O3. It's an allotrope of carbon. Very good up in the stratosphere, protecting us from harmful radiation, but not good down on Earth and just pollution. So we have 18 electrons here, 6 for each one. And we must have a bond, at least one bond between them. That makes, we remove 4 electrons. We have 18, let's get 18 there. Minus 4 is 14. So assign 2, 4, 6, 8, 10, 12, 1 on the central atom. And guess what? No octet in the central atom. So we're going to do what we did before. We're going to borrow a pair of electrons here and form a double bond. And we get O, double bond O, O. And we'll draw these electrons in. And remember, there's a resonance structure of here. It's neither structure is right. It's some combination of the two. But here's the thing I want to point out to you. Around this oxygen, there are 3 bonding domains. There's a double bond, a lone pair, and a single bond. 3 bonding domains allows this to approach the trigonal model, 120 degrees. And this third domain, you say, well, where's the third bond? There isn't. There's this lone pair of electrons here pushing around. So this angle here should be 120 degrees. In fact, I think it's about 118 degrees because the electrons push a little bit on these bonds, push them together a little bit. That's pretty bad print, 118 degrees. So this is an example, starts with trigonal planar concept, but because we have no atom out here, it becomes just a bent molecule, ozone, not linear. We'll stop there. You may want to study VSEPR model in the other session, session 1.